Okay, so we're all here these 3 days because it seems there's something very special or amazing about statistical learning, and we're all here sort of to ask why. So one reason I think it's so enthralling, at least specifically to me, is that these amazing little creatures, and this is my little creature, are able to do it. So in fact, they seem to effortlessly, even automatically extract meaningful information about our information-dense world. So the question I want to tackle today is, what is statistical learning? We've all been asking it, but specifically, what is it from the perspective of classic learning and memory systems? In large part, because these small humans are able to seemingly, even automatically, learn so much via statistical learning, the consensus has somewhat been that statistical learning is a form of unconscious implicit memory. In fact, a lot of the articles we read about this sort of open with statements such as these in order to get editors really excited about publishing our work. I've done it myself. Of course, there's also work showing that statistical learning can occur when you are focused on different, so non-intentionally taxing tasks, and that learners are not able necessarily to specify what they have learned, or at least verbalize what they have learned via statistical learning. So today I'm going to ask if this is the full story, specifically in the context of development and humans changing minds and brains. So very briefly, and I don't have to do this as much as I had initially thought because of Daphne's beautiful talk yesterday, but I want to review a classic view of learning and memory. Maybe we want to smash this view. I've sort of had a few conversations with people about various ways to go about doing that, even since arriving here. But I still think it's useful to sort of go through this model to sort of clarify exactly how we have been at least thinking about statistical learning. So here, memory is typically divided into two major subsystems, declarative and non-declarative. So people talk about declarative as the verbalizable or explicit memory system, and non-declarative as the non-verbalizable or unconscious implicit memory system. And statistical learning is typically placed in this bin, although there is increasing evidence that this might not be the best place, or at least not the only place for it. So for example, there's elegant work by people in this room, Laura Batterink in particular, showing that after having statistical learning experience, it can leave explicit or declarative traces since confidence tracks with our two alternative forced choice judgments, alongside these more non-declarative or implicit traces based on these reaction time measures that we've now talked about a few times. Also, insofar as attention is accepted as being a declarative process, it has long been shown that statistical learning can be attentionally gated, at least in adults. And finally, we do not see clear evidence for statistical learning being purely implicit from a neurobiological perspective. As each of these regions, so I'm sort of drawing your attention to the medial temporal lobe or the diencephalon, where the hippocampus lies, the striatum, and the neocortex have all been places that have been, at least in functional neuroimaging studies with adults, implicated in statistical learning. So where does this leave us in terms of where to plot statistical learning? And again, maybe that's not our goal, but I want to at least outline all of the places where we can plop it and talk about the ways in which these systems interact to produce this wonderful learning system we're all here to talk about today. So in the 20 to 22 minutes I have left, I will attempt to answer at least two slightly more tractable questions within this larger space. So first, I'm going to ask if statistical learning is a purely implicit cognitive process. And although we already have a sense that it's not, I want to further probe how statistical learning squares in terms of what we know about foundational properties of declarative systems that I've sort of just shown you. And specifically, I want to look at how information decays over time and whether it's subject to capacity limitations. Second, I'm going to ask about the neurobiology of statistical learning and ask whether this is purely implicit. And here I'm going to take a developmental lens and maybe inundate you with another theoretical framework that I am very excited about in other work about asynchronous development of a lot of these neural substrates that are important for our learning. And so within this lens, I'm going to look specifically at how statistical learning might change, or the neurobiology of statistical learning might change with development. And so to that effect, I'm going to try and present to you 3 experiments over the course of the next, 19 minutes. And in the first, I want to explore very carefully decay and testing effects within the context of statistical learning. In the second, I'm going to explore whether statistical learning is subject to a capacity limit, and talk about whether everything we're exposed to is something that we end up learning. And then I'm going to transition to talking about development and the brain. So it's very exciting. I haven't actually talked about any of these 3 experiments to a large audience before, so your feedback is very welcome, and I'm excited about the conversations I get to have with you guys later today. So experiment 1 is a collaboration with the lovely undergrad Helen Luke, pictured first, and Catherine Duncan, who is one of my lovely colleagues at the University of Toronto. Daphne Shahami showed you her picture a couple times yesterday, so she'll be excited to know that she made various appearances here today, but actually traveled in Spain. Okay, so in experiment 1, the question I'm going to tackle is, are direct and indirect measures of statistical learning, which are thought to map onto implicit and explicit traces. And Kevin did a nice job of sort of outlining that already for me yesterday, what an indirect measure is, what a direct measure is, how this mapping probably works out within the context of what we think about cognition. I'm asking whether those are dissociable. And since we know these traces, explicit and implicit, declarative, procedural, whatever your favorite label, decay at different rates and can be differently responsible to testing effects, we're going to aim to look at these factors specifically. And I'll talk about that within the context of my experiment more specifically. So what we did was we recruited 60 adult subjects, and we exposed them to a non-segmented speech signal. So it's a natural statistical learning stream, similar to what you've heard. I'm going to show you the stimuli in just a minute. But the paradigm with which we exposed individuals to this was there was an initial exposure phase where they sort of listened to this language passively over headphones. After they were done, they completed an immediate test. And the immediate test was broken into 2 components. So there was this direct test, followed by an indirect test. So the direct test I'm going to talk about in a little bit more detail in a second. And the indirect test was this reaction time-based measure. And crucially, we only tested, during this initial test anyway, we only tested half of the information that they were exposed to. And then they came back 24 hours later, and they completed the full test. So first, again, the direct test, and followed by the indirect test. And they were interleaved with unique and retested information, right? So half of the information they experienced during this delayed test was information they had been tested on before, and half was entirely unique. They hadn't been tested on it. And this is going to allow us to sort of unpack some of these crucial questions about whether these different traces have different susceptibility to testing effects. Okay, so there were more words than is maybe typical in most statistical learning studies. So we had 6. Again, this is because we wanted to be able to measure certain things immediately and during a delay. It's still not a ton. From an episodic memory perspective, you probably want a lot more than this, but this is what we did. And then we had various foils. So during the episodic memory test, their task was basically to say whether a word that they're experiencing was new or old. And so a third of what we exposed them to were these actual words right here. They were also exposed to what I'm calling shifted foils within the auditory stream. This is very similar to what we typically call part words, right? So you have one preserved transitional probability and one transitional probability dip within the context of those. And then we have these position match foils. So within the visual statistical world, these are your typical foils, like what Nick Turk-Brown tends to use, where what you're doing is you're matching the position of each of the items, but all the transitional probability information is nil, right? So you never experience go after ta, but ta is always in first position, although in this particular example, yeah. And go is always in second position, and B is always in the third position. Does that make sense? These are? Okay, so in our direct test, all we're asking them is what you're listening to a word that you've experienced before during the exposure or not? Is it a non-word? And how confident are you about that? And we have them rate that on a scale of 1 to 5. our indirect test was this syllable detection in stream position. So this is the target detection task that Kevin was talking about. It's a little bit different in our hands. So the stream we're looking at here in which they're detecting is much longer, but we have a lot of the important controls in place that Kevin was talking about. So the first thing I want to show you is that performance on these direct and indirect tests is not related. Again, this isn't new information, right? Laura Battering has shown this to us, and even Kevin yesterday showed this to us. This is a very consistent finding. So I have a measure of direct recognition along the x-axis here, and a measure of indirect speeding. So this is basically the indirect test. What we're doing is looking at speeding from position 1 to position 3. So believe me, I'll show you learning in a minute. But the point of this figure is basically just to show you that these measures are not related, and we have like nice variation in both in order to observe that. And that's true on the information when it's tested first. It's true when the information is retested, and it's also true when the information is uniquely tested during the delay period. Yeah? Okay. So maybe we're measuring separate things. So to go through the data on the indirect test, we observe, so first of all, in pink is the speeding as a consequence of when you were first tested on this, so just immediately after exposure, and we see significant speeding there from 1 to 3, so I don't know, maybe this is making people feel better after Kevin's talk if you use this measure, but again, this is within the context of an auditory domain. And then in blue, we have the retested information that was acquired during that delay. And again, you see significant speeding, and also for the uniquely tested items also during that delay. And so what I want to visualize over here is actually that what we're observing is a strengthening of these implicit memories over time. So again, what I'm plotting you here is just the R2 speeding. So this is that 3 minus 1 index that we're used to sort of looking at in this context for the first, for the retested, and for the uniquely tested information. And it actually gets significantly better over time. And there are no testing effects here, right? So there is a strengthening of your implicit trace over time, at least over a day. And there are no testing effects. So it doesn't matter if you tested that particular information immediately or if you did not. It seems to just strengthen. Which I think is pretty cool, and I'll talk about in a minute. So now the direct test. So here we actually show that explicit memory is displaying clear testing effects. So again, in pink are the data for when the information was tested immediately, and along the y-axis here I'm plotting D prime. Blue is retested, and green is unique. And so when you look at everything together, considering both those shifted and those position matched foils, what you observe is a significant testing effect. So some kind of consolidation mechanism is probably at play here, boosting the retested information, where it's actually better when you're retesting it the next day. And there's a drop in your performance on the uniquely tested information. But we wanted to see, for various reasons, I think that Tess will talk about very shortly, and also for lots of controversies that have been discussed here today with regard to transitional probability and chunking representations, we wanted to see what these looked like when we separated for our different foil types. So remember, in our shifted foils or our part words, we actually have a preserved transitional probability. So there's some signal within those foils that is slightly word-like. And in the position matched foils, the only signal that is at all old is position. And we wanted to see if these sort of differ. So in the shifted foils, what you see is, again, a testing effect, right? So there's a difference between the retested and the unique information relative to the first. And what's really interesting about this is that you're actually not treating this unique information as different from the actual words unless it's retested. If it's retested, you can preserve that information, but if it's not, then it's gone, and you actually don't distinguish a part word or a shifted foil from an actual word that you experience. So the way I interpret that is the signal that's left in that one transitional probability information is enough to sort of make you think that that's a word a day later, unless you've tagged it for some kind of consolidation. Does that make sense, everyone? Yeah. And then in the position matched foils, what we see again is this testing effect. So retested information is better than uniquely tested information during the delay, which is quite different from our shifted information, right? So these position foils, you could, I think of them as like amazing foils because they distinguish the word information nicely from the non-word information, or you can think about them as having like no signal that basically fools the learner into thinking it's word-like. So explicit memory shows clear testing effects, and what I think this means is that representations of detailed syllable structure fade. So shifted foils are treated as words. So within this more direct or explicit domain, the representation of what you're experiencing is less veridical, especially when you use a foil that's slightly overlapping with what was experienced in terms of transitional probability information. Yeah? Okay, so I wanted to directly compare these traces, these implicit and explicit traces, in particular in terms of the consolidation, so the change from when we first tested them to when we tested them a day later. And so to do this, we normalized our indices, so D prime and response speeding separately to place them on the same scale, and then participants D primes and response speeding across all testing conditions, so first, retested, unique, were subtracted. So the z-scores were subtracted first from retested, first from unique, retested, it's actually retested from first. So a high value means greater performance during the retest, and a low value means worse performance during the retest. And what I have shown you here in peach is the data for the indirect, and it's on both of these graphs. It's literally exactly the same data, right? I don't have shifted foils or position match foils for the indirect test. And then in purple, I'm showing you the direct information. And so what you see here is that for the shifted foils, on the retested information, there's not much decay, right? But compared to the indirect measure, it's not getting as much better, basically, as the indirect. But the most interesting finding within this context, I think, is right here. So you actually have the implicit representation getting stronger over a day, whereas the explicit representation, when calculated relative to these shifted foils, is getting worse unless you take uniquely tested information. And worse, like I said, insofar as your ability to distinguish it from an actual word. And these trends exist within the position match foil data, but not nearly to the same extent as here. Okay, so explicit representations are less durable, but only in these very specific contexts, right? So what does this experiment mean? It means that we have both implicit and explicit representations after a statistical learning experience, and that these are clearly dissociable. So again, Laura already showed us that they're not necessarily correlated, that we can have both of these traces. But what I'm showing you is that they also, in a sort of experimental way, they decay differently. So implicit strengthens, and these detailed explicit representations actually decay. And I also showed you that testing effects impact the consolidation of explicit information, but not implicit, which is pretty interesting because basically what this is saying is that what happens after the original learning experience actually modifies the representation of the explicit information, but not the representation of the implicit information, right? So you have this like more malleable representation. And I want to just take a few liberties because I think we're here to have fun and talk about what I think this means. And I'm going to go a bit beyond my data, and you guys can ask me about that later. But these findings have sort of made me think in new and exciting ways about sort of what happens after statistical learning. So let's say we have two representations. I think I've shown you we have two representations. One, the explicit, is malleable, right? We're seeing these testing effects. So what you do after a learning experience in this explicit trace actually changes the nature of the trace. If it's not tagged for consolidation, and it's fuzzier. So if you preserve one of two transitional probabilities, you actually don't see that as different from a word that has two preserved transitional probabilities. And I probably don't get to talk to you about this for as long as I'd like, but having this fuzzy or more abstract representation probably is helpful, at least we think so in the context of episodic memory, when we talk about schemas and representations as being really an important mechanism for generalization. And so there's a lot to test within this framework to decide whether that's true. But what this means is that you have one more vertical representation of what you've experienced and this other sort of fuzzier representation that might help you make novel predictions about what you're going to encounter in really exciting ways. And I think most of us in this room are really excited, especially about that generalization mechanism. I don't think most of us would actually plot the generalization mechanism right on top of what we deem explicit or declarative traces, and so we have a lot to do to sort of figure out how that works. But I want to take a minute, I don't have any child data here, to talk about what this might mean. So I noted that in other work, I discussed asynchronous development of important structures, and what I've shown, and along with others, is that there's great change in explicit or declarative systems, right? So I've worked on working memory and episodic memory, and those systems are super slow to come online during development. They're present even in infancy, but they grow and get better and better. Whereas there's little change in these implicit or procedural systems. So I and others have looked at this, and these have been thought to be sort of non-changing or developmentally invariant. And so what you might have, and what I want to test, is children who have representations that are potentially less malleable. They might have more of this implicit representation, less of this explicit after a statistical learning experience, and less likely to be applied in novel contexts, so potentially more specific. This is actually the opposite of the way that I have historically thought about maybe how children are doing statistical learning differently than adults. But it's a clear and direct prediction that falls out of all this. So it's like literally the opposite of the way Rebecca Gomez has talked about how infants do statistical learning. She thinks they have a more general and abstract representation, and I'm happy to talk about that. I actually think there's a totally separate forgetting mechanism at play. And I'm talking more specifically about children, not infants here. But I'm really interested to see what your ideas on this are, and Tess is actually going to be giving a talk later in this session that provides some preliminary evidence for this idea. Okay, so I'm going to quickly-ish go through capacity limits. So this is work done by my graduate student Tess Forrest, who's here in this room. And basically what we're looking at here is taking a different angle on thinking about implicit, explicit nature of statistical learning by thinking about a different property of various explicit systems, and that is that they tend to be capacity limited. Okay, so I don't have to do much to argue for all of you that working memory is capacity limited. There's lots of famous papers about that, 7 plus or minus 2, maybe we've reduced that to 4, those capacity limits across childhood, and these change. We also know that attention is limited, right, in terms of what we can focus on simultaneously. This is also a very developmentally variant system. And a declarative memory, the idea of a capacity limit there is actually much more controversial, but I would say that the entire field of episodic memory is obsessed with trying to understand why we remember only certain things over others. And so the fact that we don't remember everything is, in some sense, a capacity limitation. And so what I wanted to ask, or what we wanted to ask in experiment 2 is statistical learning subject to a capacity limit? So for this, we studied 120 adults. I've also studied 120 children, but there's no time to talk about them today, so ask me later. And we did something actually quite simple, just as a first step. So we have a slightly more complex visual statistical learning paradigm in which there's 2 simultaneous structures present. So we have triplets at the level of shapes. So these are your shape triplets, a la Fisher and Aslan stimuli. And then we also have triplets at the level of color. So just the color on the background of these also occurs in a consistent triplet structure. And we expose people to this learning stream under 3 conditions. So the no instruction, the learn patterns, shape or color. So you just learn 1 pattern, and then the learn 2 patterns. So try to learn shape and color. Okay, so there's a color test in which, in green there, you have your correct color triplet versus one that's incorrect. Note here that the shape information is consistent across both of those foils. And then you have a shape test in which you have correct shape information, incorrect shape information on the other, and then the color information provides no cue for you. And we have 2 metrics where we're asking how many, right? We want to know about a capacity limit here. So that's our primary question. How many structures are learned? 0, 1, or 2. And our criteria, we set this at various levels. So I'm giving you the lowest level here, the 60% criteria. So if you get 60% above on this, I'm going to give you credit for having learned either the shape or the color. We did this at 75 as well, and various others. But I wanted to be liberal here. And then I'm going to ask how well are these structures learned. So the classic percent correct on your best and worst. And these graphs are actually really complicated and I don't have a ton of time. So I'm going to walk you through this first one and then not walk you through them after that. And basically just show you, we did some non-parametric statistics. So to do this, we shuffled the actual responses, the incorrect or correct data on those color and shape tests 10,000 times, thus keeping the performance exactly the same as in our observed sample. And then for each simulation, we calculated the number of 0, 1, and 2 learners using the same cutoff for the observed data here, so 60%. And this allowed us to create a distribution, so I'm going to show you this here, of the number of 0, which I'm showing you here, 1 and 2 learners that you would expect by chance given the level of performance on this task. So what I'm plotting here is just a histogram of this chance distribution. The x-axis just represents the number of simulated learners who were classified as 0 in this case, or 1 or 2 learners, of the total of 32 in this particular condition. And the y-axis represents the proportion of our 10,000 simulations in which we observed any particular number of 0, 1, or 2 learners. Does that make sense? And so, for example, right, and so the actual observed value that we have is right here, and I also just wrote the number. So our actual observed value of learners here, 0 stream learners, is 2. So out of the 32 learners, 2 of them didn't learn anything. This isn't maybe news to you guys, but they weren't above 60% on either. And then what we have here for the p-value is the proportion of simulations for which simulated values are greater or equal to our observed value, right? So in this particular case, 87% of the simulations produced a larger number of 0 learners than what we actually observed. So when these distributions have a lot of color, that means I don't have evidence to reject the null. When they're super white, I have evidence to reject the null. I'm just going to put a star there. Is that cool? So we have evidence to reject the null for 1-stream learners, which means we have more 1-stream learners than we would observe by chance based on this performance in our sample. And we don't have evidence to reject the null for the 2-stream learners. How do they do on their best and their worst streams? What we see here is that there's only evidence for above chance performance on their best stream, not on their worst stream, right? So that's what I'm showing you in the dark blue. So what this means is that there are more 1-stream learners than chance, and only the best stream is better than chance. Okay, so what happens if we try to move this? If we tell them, oh, okay, that wasn't very fair, that was a super passive watching experience. What if I tell you there is structure in the shape? Or I tell you there's structure in the color for half of our participants, so now we have 64, 32 with color instruction, 32 with shape instruction. Are you able to learn maybe more, or at least learn the one that I told you about better? And what we observe here is now we have evidence to reject the null for the 0-stream learners. So this manipulation actually weirdly produced more 0-stream learners than we would expect by chance. So there's 7 of them. We almost have evidence to reject the null for the 1-stream learners, and we definitely can't reject the null for the 2-stream learners. And what we see here is, again, very good performance on the best stream as opposed to the worst stream. And so we have more 1 and 0-stream learners than chance, and only the best stream is better than chance. Okay, so this is just comparing across the 2 experiments. So basically, you just have to believe me here. Again, a lot of white means we can reject the null. This is about the impact of the instruction on our manipulation. And what I'm showing you is that the pattern of data from the first experiment, the no instruction experiment, to the experiment in which we told them to try to learn 1 did not change. However, we were actually able to boost their performance on their best test. So you can see that here, but again, there was no change on their worst test. So telling them to try to learn one of the things actually made them learn one of the things better, but it didn't make them learn more streams. Maybe that's not surprising. We didn't tell them to learn both streams. Cool. So let's tell them to learn both. Hey participants, there's color and there's shape. Learn both. So what we find there, again, we only have evidence to reject the null for the 1-stream learners. When we look at the best and the worst test, they're only above chance on their best test. So there's more 1-stream learners than chance, and only the best stream is better than chance. Is this different from our first condition, the no instruction? No. But we were able to boost performance on their best test, but again, not their worst test. So there's no difference in the proportion of 0, 1, or 2 learners, but the best gets better, not both. You guys all with me? Yeah? Okay, so what this means is that we're not automatically extracting everything. I think we like to talk about statistical learning, so most of us actually are just picking one thing. Even in, I would call this a more complex environment, but I don't think most of you would think it's very complex. There's color in their shape, and they're both happening, but that's it. And we can't learn more than one when we try, but we can learn better. So we can't actually change the amount of information we're learning, but we can actually improve how well we learn what we do learn. So more explanation is needed, but similar to other declarative or attentionally mediated processes, we're observing some kind of limit. Okay, I maybe was a little ambitious, and I don't have a ton of time to go over development in the brain, so what I'm just going to show you really quickly is that I taught some kids a language. They were 5 to 8 years old, and I looked at just structural correlations in terms of their behavior across the brain. So they learned the language, and I'm just going to show you very briefly that their learning performance was correlated with recruitment in the prefrontal cortex. It was correlated with recruitment in, I'm not going to call it recruitment, with structure, with the size of their right hippocampus. But it was not actually related to recruitment of the basal ganglia. And I want to talk about this more because basal ganglia used to be our favorite substrate for implicit learning, at least for proceduralized aspects of motor learning. And I have lots of thought about that. But we find that it is actually not associated, at least with individual differences in structure during childhood. So what I found here is that childhood statistical learning is actually associated with hippocampal and prefrontal cortex, and these neural substrates are actually classically implicated in more declarative and explicit processes. Daphne set that up beautifully yesterday. She also helped me start to smash it, right? So there's computations that these regions are performing that may not be entirely explicit or implicit in nature. And there's a lot of work to do in terms of investigating the functional and representational changes that underlie different traces. Tess is actually currently scanning kids so we can understand more about how that works. Okay, so I'm going to conclude here. What is statistical learning? That was the big question we started with. I will say that it results in implicit and explicit traces, that these are dissociable, that one lasts longer, and one is more malleable. And I think this is really cool. It actually leads to this testable prediction that children will end up with greater implicit, because they have greater procedural capacities relative to their declarative, producing longer lasting information that generalizes in fewer contexts, so more specific representations, which is, again, very counterintuitive to the way we tend to think about kids. I showed you that statistical learning capacity is limited, so we're not automatically absorbing all of the input. I was surprised by that. I guess a lot of you aren't. But when I was first falling in love with statistical learning, I was excited about it as this way of absorbing structure from our environment, that we didn't have to do much to do, and we just would learn all the structure automatically. That seems not to be so true. And statistical learning is associated with declarative brain structures, so even in children. Thanks, Mela.